So, last lecture we have discussed about zeroth law of thermodynamics and implications of it in temperature, how zeroth law actually can give us a sense of temperature. So, today we are going to understand what is the microscopic basis of this temperature. So, before that we will just do a summary of zeroth law. So, one or more objects in thermal equilibrium has same temperature. So, we discussed that if C is in contact with A, so let us say A and C are in thermal equilibrium. So, temperature of A and temperature of C will be equal, and let us say B and C are in thermal equilibrium. So, temperature of B and temperature of C will be equal, and therefore, temperature of A and temperature of B are also equal, because Ta equal to Tc equal to Tb. However, we did not specify that A and B are in thermal equilibrium. So, therefore, zeroth law says that once thermal equilibrium is established, then a quantity which is defined to be temperature is going to be same between two objects in equilibrium with each other. Now, temperature being equal determines whether two systems are in thermal equilibrium or not. So, that is the definition again. So, alternatively we can say that if temperature is equal, then two bodies are in thermal equilibrium with each other. So, just to summarize, so therefore, a gas in contact with ice will have same temperature as that of ice, and we call that 0 degree centigrade. That is our definition. A dilute gas at minus 273.15 degree centigrade has 0 PV, V bar is 0, we call that 0 Kelvin. A gas in contact with triple point of water has a temperature of 0.01 degree centigrade or 273.16 Kelvin. So, now once we define these 2 points and plot PV, one point is 0 Kelvin, another point is 273.16 Kelvin. Once we define that, we get temperature for all the rest of the temperatures in between, because we know that it follows a straight line, dilute gas. Now, how do we measure the temperature? So, in order to measure the temperature, we bring a thermometer. Thermometer is typically can be of different types, we will discuss that, and either we measure the volume of liquid mercury that we commonly use at home for measuring the temperature, because volume will expand, or we calculate the resistance of a metal. So, that is a digital thermometer that we discussed last time, that it actually calculates the resistance which changes with temperature, and we can also measure the volume of a gas, that is a gas thermometer that we discussed. However, it still leaves us with some questions, that what is the microscopic basis of this temperature. So, why two bodies are in contact with each other will have thermal equilibration, and so that question we have to understand, and in order to understand that particular question, we will first take a gaseous system, a system in which the gas particles are there in a dilute limit. Let us say take the pressure to be very low and the gas molecules are randomly distributed within that. So, when the gas particles are inside that particular box of some volumes, what do you think should happen? The particles will move around at that particular temperature, right. So, this kind of situation will arise, where different particles will randomly move around within a particular closed volume. Now, we cannot really see a gas molecule, because they are too tiny for us to see. However, we can mimic the situation by a similar thing. So, we have a demonstration set up early for you to mimic a situation in which gas like random particles will move around. So, we are going to show that. So, you see, this is a box, you can think of that as a particular box of gas molecules, and in order to mimic the gas molecules, we have used thermocol balls of different colors. So, these thermocol balls at normal temperature, or right now the temperature will be 300 Kelvin, 27 degree centigrade, it will not oscillate, it will not move, tiny particles will move. This mass of these particles are too high for it. So, therefore, we are going to induce flow of air inside this chamber and mimic a situation how these things would have moved if they were very tiny particle in a particular box. So, we are going to place it. Okay. So, now we are going to flow air through this. Are they moving randomly?
If you decrease that, then information will be slow.
So, okay. So, now if we change the force of air flow, then the motions will be faster and more random it will be always, but it will be much faster and hitting the wall of the chamber much faster. So, here in these situations, in order to understand that what actually happens when it does that, let us say we are going to now consider two opposite side of that particular wall. So, this is mimicking the left wall and this is mimicking the right side of the wall. A particle that moves, it will go hit the wall and come back, right. So, we can calculate the force acting on this particular wall, and then we can calculate the pressure. We know that pressure is force per unit area. So, once we calculate the force, we will be able to calculate the pressure that is acting on this particular wall. So, what do we know about force? Force is something, is change of momentum. So, let us say d dt of p, p is basically nothing but mass into velocity. So, then we take the mass out and d dt of v, which will give us ma, and we know that force is equal to mass into acceleration. So, change of momentum is basically force, that is what we have shown in this particular line. Now, also you can calculate that how much time it will take for the particle to change its momentum. Now, if the length of the particular box is L and if the velocity, let us say take all the velocities to be same, if the velocity of the particle is v, then the time taken to hit the wall will be 2L by v. So, because a particle will have to go, let us say it starts from here, it will have to go till this much L, come back L, and then only it will again reverse back its momentum. So, therefore, in order to change the momentum, it has to travel 2L distance, and assuming the velocity of the particle as v, we can calculate the time to be distance by velocity. So, that is 2L by v. Therefore, the rate of change of momentum will be 2mv divided by 2L by v, which comes out to be mv square by L. So, now we know how much force is acting on one side of the wall. However, remember that in a particular cubic box there are 6 sides. So, this force that we have calculated right now is for only one 2 sides or one direction. So, therefore, on an average only 1/3 of the molecule will actually hit one side of the wall, because there are 3 different directions. So, force that is acting is mv square by L. So, pressure we know to be force per unit area, and pressure will be force per unit area, which is mv square by L into A, and A is nothing but is a cubic phase. So, L square giving rise to mv square by V. So, mv square by V is the pressure that is acting on one side of the wall in one direction. Given n number of molecules, 1/3 of the molecule will actually go along x direction, 1/3 of the molecule will go along y direction, and 1/3 will go along z direction. The reason being, since the particle motion is random, there is no preferred choice of the particle to go to one side. Therefore, in order to calculate that, so now before we say that Pv equal to mv square, because we can multiply V with P, and then for n molecules Pv equal to n by 3 mv square. See, this 1/3 factor is taking into account that we are only taking on an average 1/3 of the molecules. If there are n molecules present, then the force that is going to be acted on the wall, on one side of the wall, will be 1/3 of mv square. So, now we have this equation which is Pv equal to n by 3 mv square, and we already know from our previous discussions of a dilute gas or ideal gas situation is that Pv equal to n kBt, that we have already established. So, therefore, equating these two equations, we are going to get n by 3 mv square equal to n kBt, which means now if I cancel our n, which is 1/3 mv square equal to kBt. So, therefore, temperature is nothing but average kinetic energy of the molecule. So, here 1 by 3 mv square equal to kBT. So, therefore, half mv square is equal to 3 by 2 kBT. So, we see that Kb is Boltzmann constant that we know already. One thing just I wanted to mention here is that we have studied PV equal to RT. So, that is true when you are talking in terms of moles. However, when you talk in terms of molecules, then R is nothing but Avogadro number of molecules multiplied by Kb. So, what we get here is that 3 by 2 kBT. So, now Kb is a constant. So, therefore, T is proportional to half mv square or kinetic energy. So, temperature is nothing but kinetic energy for at least for the gas molecules. Now, does it mean that all the particles are moving with velocity v? Because we have what we have considered here. We have considered that particle velocity is v, just one value of v, and we have done our calculations. Now, it turns out that all the particles will not have the same velocity v. It is very improbable to have all particles velocity v. So, that is the work of first Bernoulli and then Maxwell and Boltzmann, Maxwell-Boltzmann distribution, that shows that there will be a distribution of velocities at a given temperature. So, here we are showing that Maxwell-Boltzmann distribution of oxygen at different temperature, and at one particular temperature the curve is like this, which indicates that there are particles with smaller velocities, there are particles with much larger velocities, and there is some most probable velocity also is present. So, what if we do a very sophisticated calculation in which we consider all possible velocities of those particles, then we can arrive at this particular equation of Maxwell-Boltzmann velocity distribution, where this equation, if you plot, it look like this, which says that there are few particles with smaller velocities, there are few particles with much larger velocities, and most of the particles will have a velocity which we call as most probable velocity. So, distribution of velocities is determined completely by mass of the particle, and if we calculate the average velocity, then we can show that we can write that average velocity of the particle as root over T by m. Just to clarify, the velocity here is actually nothing but the speed of the molecules, which does not have any directions, it has only the magnitude. So, it is obtained by taking the average of square velocities and then taking the square root of that. So, subsequent discussions, when we mean velocities, actually we mean speed of the particles. Individual velocities we cannot really consider, but the formula that we are going to ultimately use considering all possible velocities is that it is the half m v average square. So, if I use this, then it is half m v average square is proportional to the temperature. So, it is not one particular velocity that all the gas particles will have. We are going to consider the average velocity of the particle, and still the equation will remain true, and also it indicates that if the temperature is higher, the velocity of the particle will also be higher. So, temperature is nothing but then average velocity of the particle when we are talking about gas molecules, at least, because all the derivations that we used, we assumed that these are random motions and it is hitting the walls and creating the pressure on the walls. So, in order to show that velocity is indeed going to be proportional to root over of temperature, we have carried out the simulations of gas particles at different temperatures. So, we are going to show you that. So, the left hand side, the gas molecules are at 300 Kelvin, this system is at 500 Kelvin, and this system is at 700 Kelvin. So, you can see from this movie that as the temperature increases, average velocities of the particles are increasing. There is a change in the speed of the particles as such, although it may not be very apparent looking at this. However, if you just compare the lower and the higher one, then you can see that there is a big difference. So, that indicates that all these particles, if you actually really go and calculate the velocity of the individual particles, all of them will not be having the same velocity, and all of them will not be moving with the same of course same velocity. However, if we now calculate the average velocity, we will see that as the temperature increases, the average velocity of the system increases. So, this we have understood that when we have an object close to another object, we can measure the temperature. We have understood that. Yeah. Okay. So, the question is that if you give heat and then for enough long time from all sides, whether the distribution will be same or not. Okay. So, to clarify that question is that all that we are talking about is when the system is equilibrated properly, when you give heat from all different directions and let it be in contact with a reservoir of a particular temperature, and when the system comes in thermal equilibrium with that system, then only we will get the Maxwell-Boltzmann velocity distribution. So, the distribution of velocities in which you have several possible velocities is in fact when the system is in equilibrium. So, it is the property of the equilibrium that all the particles will not have same velocity. So, that is why it is not possible to have same velocity for all the particles. So, the nature of equilibrium is such that it will have the Maxwell-Boltzmann velocity distribution. It cannot have all particles having same velocity. Okay. So, that is the property of the equilibrium itself. So, all the thing that we are talking about in this particular class in thermodynamics, they are all pertain to system in equilibrium. We cannot really talk about anything that is out of equilibrium. So, the fact that with temperature the velocities are higher will have its own consequences. For example, when we have a mixture of two different gases or liquids at two different temperature, the mixing rate will be of course different, because molecule will move faster or slower depending on the temperature. So, here we are going to show you animations that when there is a mixture of two systems, one is let us say at 280 Kelvin and another is at let us say 400 Kelvin. Initially they are separated, these blue and red particles. You see as the time progresses, 400 Kelvin system is mixing much faster than the 280 Kelvin. 280 is pretty close to the ice like situation, and 400 is almost higher, a little bit higher than the boiling point. So, we are going to also show that through a demonstration here. So, this is ice cold water and this is warm water. It is not very hot. So, what is the temperature of that? Can we just measure it? .40°, just 40°, enough, and this will be okay. .20°. Yeah. So, not much of a difference, but we are going to see whether it works or not. So, without shaking, we want to take it here. This is a cold water, this is hot water, and the ink particles are actually going to be distributed. In order for it to be distributed, the ink has now become in thermal equilibrium, ink has come to thermal equilibrium with the water. Now, it is going to have similar distribution of velocities that is there in water for the ink particle as well. You see here the spread of the ink indicates that the motion is higher when the temperature is higher compared to when the temperature is lower. Correct. So, the question is that if now the particles will have different size, how does that affect? So, the thing is that when we are talking about very dilute gases, which is also equivalently we can say ideal gas, then size will not matter, because size only matters when you have interaction with the particles. But if you said that mass is different, then obviously there will be a difference, because our velocities will be proportional to mass and temperature. So, if the mass is heavier, then the velocities will be smaller for a given temperature. So, it will move slowly at even the same temperature. So, hydrogen and oxygen when mixing together, hydrogen of course will move faster at that same temperature, because it goes inversely proportional to the velocity. Was that your question? Okay. So, Boltzmann distribution or Maxwell Boltzmann distribution is it is okay, I have to be very clear here. So, Maxwell Boltzmann distribution for a given temperature. So, let us say you bring a gas bring a chamber full of gas molecules in contact with a reservoir having certain temperature. Let us say our room is a reservoir, you keep a box. When you keep a box full of gas molecules, so the system will now come in equilibrium with the surrounding having same temperature. So, system temperature is same as the outside temperature because it has come in thermal equilibrium. Now, if you pick individual gas molecules and calculate this velocity, you will see that their velocities are different, and now you are going to plot all the velocities, you are going to find Maxwell Boltzmann distribution. So, when there are macroscopic variables, so we talked about macroscopic and microscopic variables, right? Volume, temperature, pressure are macroscopic variables. So, given a fixed macroscopic variables T same, the microscopic variables like velocities going to have a distribution, not one value. Okay. So, similarly when you talk about this particular hot water, so the temperature is fixed right now, let us say at 40 degree. However, the velocities of these water molecules are all different, having a distribution. They will not have, all the water molecules will not have the same velocity, there will be a distribution. So, the equilibrium enforces that there will be a distribution of velocities, and it will be clear later on when we talk about entropy that why that happens, why not all of them will have the same velocity, why by nature itself will choose to have all different possible velocities. So, the question is that whether a mixture of gases will have Maxwell Boltzmann distribution or not, right. Yeah. So, as long as the gases can be treated ideally, which means the interaction is very less, or you can say dilute gases, it will follow Maxwell Boltzmann distribution.
So, the nature does not matter as long as there is no chemical interaction.
Nature does not matter as long as the interaction is, or it is a very dilute gas. If there are different masses present, then as you see that in the equation there is a mass here, right. Yes. So, you are asking that what will happen to mixture of that distribution, right. Yes. So, it will be a mixture of these two equations. So, it will be a mixture of two Maxwell Boltzmann distribution. So, one Maxwell Boltzmann distribution will have, so for example, I can write m1 by 2 pi kBt to the power 3 by 2 4 pi nu v square exponential minus m1 v square by kBt, and let us say you have another one, let us say the m2 is very large compared to m1. So, what is going to happen is that you are going to get two distribution, one corresponding to m1 and another corresponding to m2. So, individually, so if the masses are equal, then it will fall on top of each other if the temperature is also equal. However, if masses are different, then it will be shifted. So, it will be a mixture of two Maxwell Boltzmann distribution. That is a very good point. Right. So, the question is that why we took very simplistic assumption that the length is 2L, the particle can zigzag, have a zigzag motions, and the length can be this thing. So, as I said that it is a very simplistic approximation. So, the simplistic approximations are in two forms. One is that we have taken a straight line and then we have considered also same velocities for all the particles. It turns out that even if we did not do that, result would be still same. Although we have taken a very simplistic description here, if you took a complicated descriptions of all possible random velocities and all possible pathways, it would still give you the same answer. So, now the another question is that particle will interact with each other and therefore, it may not even reach the wall. That assumption we have already taken into account by saying that we are talking about extremely dilute gas system or ideal gas in which there is no interaction among the particles.